Let's get started. So my name is Jose Garcia. I work at the WCEC, and I've been working there for 4 years. And today I'm going to present to you on the feasibility study of a water-free adsorbent pre-cooler. So some background for the project. Cooling loads are a major driver of summer energy consumption and peak demand in California. Evaporative pre-cooling can increase the performance of an air conditioning system by reducing the condenser air dry bulb temperature. And prior research suggests that evaporative pre-cooling can reduce energy consumption by 10% and peak demand by up to 20% in climate zone 10 in California. So for this particular project, we were interested in how can you pre-cool without using any water? Because a lot of these climate zones where evaporative pre-cooling is effective have water scarcity problems. Climate zone 10 would be Riverside area. It's in SCE territory. They're, yeah, pretty close. Yeah, so the basic concept is, can you evaporatively pre-cool without using water from a water supply? And so some of the benefits of pre-cooling with the adsorbent material: the water supply for your device is actually moisture in the air. You don't have to worry about bleed water degrading system performance due to scale formation or treatment of the water. And this is kind of a drawing here of what this device would look like before it is attached to the condenser coil. Some of the challenges of pre-cooling with adsorbent material: the strategy relies on a large diurnal swing for charging and recharging of the device. There's a trade-off between the system size and the overall cooling capacity because it effectively stores all the water it uses the next day. So you could end up with a large device in order to actually meet the cooling demand for a day. Manufacturing the system could be expensive, and currently there needs to be more research to understand how the channels can be manufactured. And currently the adsorbent material is very expensive. It costs about $300 to $500. We expect the price to drop by an order of magnitude. There's research going on into that right now. And let's see.
Metal organic framework?
Yeah, these are metal organic framework materials. Yeah. So this project started with a literature review of the adsorbent materials and a material selection. The literature review was conducted just to get a list of possible materials that we could use in the device. And we selected 8 materials for further study. And for these materials, we performed a regression analysis on the available adsorption isotherms for these materials. And we built a function called a Langmuir function. And what this allows you to do is understand the equilibrium loading of the material given the relative humidity and the temperature. So some desirable traits of these materials include high maximum loading fraction. And what this means is that if you can store more water per kilogram of material, then you need less material to provide the same cooling. And you also want material properties such that the material can be charged at night and discharged in the day. And on the next slide, I'll show you what that means. So we decided to use MIL 101, which is this material here. This is a curve of the equilibrium loading fraction at 86 degrees Fahrenheit. Down here on the x-axis, you have the relative humidity, and here you have the equilibrium value of loading. This is in kilograms of water per kilogram of metal organic framework, the material that we're using. So over here, you'll see this is a very undesirable material because the usable range is effectively 0 to 2.5% RH. So that's not going to be useful to you in a device that you can't capture. You can't capture an unloading and reloading cycle with a reasonable climate. By the same token, these are undesirable as well because these have low maximum loading. So your equilibrium value of loading is around 0.2 kilograms per kilogram. So you're going to need a lot more material to store a decent amount of water in them. This MIL 101 G06 is actually better than what we decided to use. But we didn't use it because there's limited research on it, and we wanted to use a material that has more research so that we had a more solid standing to do this project. So we went with mill 101. So you can see that it's fully unloaded at about 30% RH, and the curve here goes up to about 60%, at which point it's fully loaded. So in between 30% RH and 60% RH, the equilibrium value can be anywhere along this curve. So basically the way it works is at night, your RH actually goes up. It's going to be greater than 60% in most climate zones. And so you're going to, if you're pushing air through the device, you're going to load it with water because this is the equilibrium value of loading. And in the daytime, when the RH drops, hopefully close to 30% or 40%, you're going to desorb a lot of that water. And so maybe if it's 40%, you're going to be able to desorb it down to 0.5 kilograms per kilogram. So that means that for every kilogram of MOF that you had in the device, you've used 0.7 kilograms of water to pre-cool the air. So I hope that that's clear. Yeah, are there any questions? Yeah, we use it. So that's one way to do it. We actually ended up coming up with a different architecture because we needed to control it better, and I have a slide on exactly how we charge it and discharge it. So we have a secondary fan as well because what we wanted to avoid is accidental charging of the device during the day, which would rise your temperature in your condenser coil. Because the device actually didn't end up being, you can't have a large enough device that's reasonably dimensioned to actually store enough water for a full day. Does that make sense? Okay. Yeah, and I'll go over it a little bit more too later in the slides. So the goals of the modeling work, we wanted to determine the ideal geometry of the heat and mass exchanger. And using that ideal geometry, we wanted to determine the reductions in energy use and the cost reductions from baseline. The cost model is based on published time of use rates for SCE, for the residential time of use rates. We have 3 rates based on peak, off-peak, and super off-peak, and I'll define those a little better later. We account for reductions in daytime energy consumption and also increase in nighttime energy use to charge the material. So the essence of the modeling work was this mass transfer model. And just to put it simply, you have a driving potential, which is your mass fraction at the surface, and it's the difference between the mass fraction at the surface of the material and the mass fraction of water in the air here. So that's your driving potential. And you have a resistance to that transfer. And so what you get as a result of that potential and the resistance is you get a flow of water from the adsorbent material to the air. It can also it goes both ways. During desorption, this is what it looks like. And at adsorption, it's going into the material. So we simplified the system for our modeling work. We neglected the resistance in the porous material and the actual material itself because we had such a thin wall that we said that resistance is low compared to the air side resistance and also compared to the vapor pressure barrier here, which limits your mass fraction at the surface. So yeah, we neglected the resistance within the material itself and also the chemical reaction rate because we did a rate study on the chemical reaction rate and the mass transfer rate. And we found that in most cases, except for when you're very close to equilibrium loading, the chemical reaction rate is not limiting. It's actually the mass transfer through the air that's limiting. Is this clear to everyone? Does anyone have a question about this? Okay, good enough. Okay, so next up, so first thing we did was a parametric variation to figure out what are the optimal dimensions for this heat and mass exchanger. And so we chose 4 parameters to vary: the adsorbent mass, packing density, channel cross-section, and wall thickness. So this is your wall thickness here. This is your cell height, your cross-section, and it's a square cell, so that makes it simple. And the length is varied as a function of all of these. So the length is defined as a function of these, and changes depending on what values you use for these. We ran the parametric variation twice. The first time we just basically guessed what the best values would be, and then for 3 of the parameters, and then varied the 4th parameter. But then when we actually optimized it, we used what we had decided was the best parameter, and then for each of the 3 parameters that were not being varied, and then for the 4th parameter, we varied that with these fixed values for. So for instance, if we were varying the adsorbent mass, we kept the packing density at the optimal value, the channel cross-section was kept at the optimal value, and the wall thickness was kept at the optimal value, and then we varied the mass. Nelson?
Is square the best shape?
Not necessarily the best shape, but the simplest shape in terms of analyzing.
I didn't know if
Right, yeah, the surface area is important. Since it's an initial feasibility study, we decided to go with the square. Yeah, it can probably be optimized away from the square, and that's definitely something that. Right, yeah. Okay, so anyway, the design concept. So some of the unique design challenges we face with this device. In order to be useful, the device has to be large enough to store enough water to have a significant impact. That large size leads to an increased pressure drop and fan power draw. And you also have a trade-off between effectiveness and pressure drop losses. I mean, that's not unique to this device. That's typical with heat exchanger design. And because the device charges and discharges in the order of hours due to size limitations, we have to control the airflow through the device in order to prevent adsorption during the day. Otherwise, there's no point in having the device because you would end up canceling out any positive effect that you had from desorption. So basically, you need a mechanical system to control the system. And so here's a diagram of the mechanical system we came up with. You have damper 1, damper 2, and damper 3. This is your condenser coil. This is a secondary fan that we have for loading the material, and basically helps us not have to go through the condenser and face that additional pressure drop at night when we're charging the material. So in mode 1, when you're desorbing, damper 1 is open, and let's see, yeah, damper 3 is open. So you're using the condenser fan to pull air through the heat and mass exchanger into the condenser coil, and it's pre-cooled that way. In mode 2, adsorption, let's see, yeah, damper 1 is open and damper 2 is open. So you're pulling air through the heat and mass exchanger at night to adsorb water into the heat and mass exchanger. And that way you don't have to go through the condenser coil. You can not face the pressure drop of the condenser coil, basically. And in the third mode, basically in the day when you've ran out of water in your device and you want to prevent any adsorption from happening, and also the pressure drop of going through the device, you just have air flowing directly through the condenser coil and bypassing the heat and mass exchanger. And I think, in my opinion, it would be best not to have the fan running, so you'd have to have just a bypass straight to the condenser coil. Does that make sense? Okay, so how did we program the controller into the model? The controller has a clock and it has 2 temperature sensors. The clock delays use of the pre-cooler until 2 p.m. and that's when the rate jumps to peak pricing, and so that's basically, yeah, that's when you start your peak pricing period. After 2 p.m., if the temperature exiting the pre-cooler is higher than the temperature entering the pre-cooler, then that means that you have adsorption, and so the device shuts off the heat and mass exchanger, the dampers bypass it, so that you prevent adsorption during the day. And then after midnight, when it's night again and you're not on peak pricing anymore, the unit's allowed to enter adsorption cycle, and if it doesn't adsorb by itself in the night, due to, anyway, we force adsorption from 3 in the morning to 6 in the morning, because that's when the relative humidity is typically the highest. It's also when your air temperatures outside are the coolest. So, some simulation parameters. Our baseline system is a 3-ton residential air conditioner. The nominal COP is 3. We developed the loads using Energy Plus, a standard 2,000 square foot reference home. The EIR and capacity of the baseline unit are modified based on the ambient conditions. And the EIR and capacity for the retrofit system are modified based on the temperature exiting the pre-cooler. And in bypass mode, it uses the outdoor air temperature instead of the temperature coming out of the pre-cooler. We define the cooling season as May 1st to October 1st, and this is the cost structure we used. I don't know if you guys can see that at the back, but peak use is 45 cents per kilowatt hour. Transitional hours are 28 cents per kilowatt hour, and off-peak use is 13 cents per kilowatt hour. And peak times are from 2 p.m. to 8 p.m. Off-peak is 8 a.m. to 2 p.m. and also, 8 p.m. to 10 p.m. Super off-peak is 10 p.m. to 8 a.m. So super off-peak is this one. Sorry, that's confusing. Okay, so these are the results. So the cost and energy reductions in terms of percentages. So you can see climate zone 10, we get to almost 5% in terms of energy savings, and we get to just above 5% in terms of cost savings. Compared to the other pre-cooler that we referenced that was from an SCE report that we produced at the WCEC, that system had a 10% energy savings. So we're almost at half of that traditional pre-cooling system. You can see that climate zones 10 and 13 perform pretty well here. And climate zone 6 does not perform well. We actually have negative savings, so that's bad. You wouldn't want to use it in climate zone 6.
Where is it?
Don't know off the top of my head, but we can look that up. Yeah, all of the coastal zones in general actually had issues with this material. But it doesn't mean that the concept's bad. It just means that maybe you can explore using a different material. Because
You don't do much cooling in the coastal zone.
right, yeah, that's true. Yeah. So these are the actual cost reductions in terms of dollars per year. So climate zone 13 is actually the best at $67 per year savings. We have 4 climate zones that are actually above $30 per year. I mean, it's pretty meager in terms of paying off this equipment, I think.
You might have said it, but
2,000 square foot. Yeah. Yeah, so, and of course, in terms of percentages, 5%, I'd say 3% to 5% is about what we're saving here.
Do your cost savings include the capital cost?
No, we didn't, because we don't actually have a hard number for the capital cost right now.
Cost.
Yeah, so this is just due to energy reductions. We're not even considering how much water you didn't use in this cost reduction here. This is your maximum demand reduction, and what you see here is actually climate zone 15 and 14. I think these are the interior, like desert zones, have your highest demand reduction possible. But the problem with these climate zones is that sometimes it doesn't actually reload overnight. Sometimes the humidity doesn't actually get high enough at night for it to actually reload. And so that's why, even though you have the highest demand reduction here, you don't have the highest energy savings overall here. Yeah, that could. Yeah, and that's something that I think that we need to do a more refined cost analysis, especially if we can get better cost numbers for the material.
And you mentioned other materials.
We can go back to the materials page. I mean, the idea would be if you have this curve shifted to the left, then you could actually use it in the desert. And if you shift it more to the right, then you could use it at a coastal zone. Right, yeah. Right, this one here. Yeah, exactly. Yeah, so this one might be better for the desert, but then of course you have to consider your maximum loading fraction is actually pretty low. Right, yeah, exactly. Yeah, and that's the hope for these materials, is that they're going to make them super cheap. But for now, this is what we're dealing with. Okay, the final slide here is avoided water use, and we just used some simple rules of thumb. From a previous pre-cooling report, we got the numbers 3.5 to 5 gallons per kilowatt hour. So we took the overall energy savings and just did a low estimate and a high estimate. So for climate zone 13, we think you could save 500 to 700 gallons per year. I think that this could be refined even further by using another pre-cooler as a baseline model and running them side by side. But this is an estimate using some rules of thumb. Conclusions. So we have energy savings in climate zones 8 through 10 and 13 to 16. Climate zone 10 has an energy reduction of just under 5%. And again, that's half as much as a traditional evaporative pre-cooler with 50 to 70% evaporative effectiveness. You're going to have additional costs due to the controller and the required hardware. And the cost of adsorbent materials needs to decrease substantially before this is a feasible technology. And obviously, Mark brought up a good point, though. The demand reduction could be significant in terms of changing the payoff point for this technology. We're using 50 in this simulation, yes. Yeah. We use 50, and it doesn't provide you. I think at one point we estimated 300 kilograms for a full to run it all day, right? Yeah.
So, but even 50 kilograms,
Yeah. Yeah.
does that change the equation?
Yeah, it does. Yeah, and we didn't do that in depth of a cost analysis, but it does. Yeah. So you have to. Yeah. So when they're designing the roof, or when they're doing the drawings for the roof, they have to consider how much it's going to adsorb as well. Yeah.
Yeah, that's true.
Well, so this one absorbs up to 1.2 kilograms per kilogram, so that's 60 kilograms. So loaded, it's 110.
250 pounds.
But you don't have to carry 250 pounds up. You could carry it up there dry, and then.
I'm not worried about your back. I'm worried about the support and the
Yeah.
civil engineers who say, okay, your system weighs too much.
I mean, how much does a typical evaporative pre-cool? I mean, it has a sump usually. Not that much, obviously, but.
They're not putting the ones that show residential applications weigh nothing.
Right. Yeah.
Sprayers, and they wrap a blanket around it and they spray water.
I wasn't at the old facility. No, I don't remember that.
You remember that? You go to compare storage.
Yeah, you have a sump. And you're saying the sump's on the ground? Or there's no sump? There's no sump, yeah. Yeah, so all of these things, kind of limit the feasibility of the... Okay, so some future work, and that's for future work, right? We have to determine all these costs. So we're working on incorporating the chemical kinetics and the porous network resistance in the model. We're doing that so we can actually publish the work. And so those will slightly change the results, but not by much, because we made pretty good assumptions that you can neglect those two effects most of the time. We have to perform a detailed cost analysis for the envisioned design, and that includes all the things that Mark was talking about. And I think that there also needs to be manufacturing research to see if you can actually print these materials or cast them as small as we need them to be in this heat and mass exchanger. Are there any questions, Robbie? Yeah, we can go back to that.
Shift a lot with different temperatures?
No, it doesn't. It's actually pretty constant with different temperatures.
Because it's our range.
Well, right, this is at at 86 degrees Fahrenheit, but what we found is that there's only a small, like, few percentage RH shift in the curve with pretty large temperature changes. Yeah.
Economics. Charging. So in a situation where you may have a storm where there's several days, very hot weather, so there's no opportunity to charge, you may not be able to use demand every day. In some cases, rains such as the Paris are not demand, but sort of average of
10 days?
for the last month.
Oh, okay.
Something the highest in the last year. So if you blow it once,
Yeah, I mean, yeah, we didn't really do a demand reduction study besides just showing you here what the demand reduction is, but
you just need to be careful about the
and maybe if the price incentives are right, maybe there would be a way to recharge it to, I mean, by using water in an extreme case so that you can actually make it cost effective.
That was my question.
Okay.
You could use water to recharge it, essentially.
Yeah, you can. Yeah, actually, so the way that they developed a lot of this data is by just immersing the material in water. So you can immerse the material in water, I assume, without it dissolving. Oh, Matt. I mean, so silica gel is one of them, and they put those in your new shoes. Yeah, and I don't really know beyond that, actually. That's a good question for Vinod. Okay. I mean, our dryer, like the dryer we have in the lab, has a. Does it have an absorption bed? Yeah, so it does. Oh yeah. Not no 101. Yeah. Curtis.
Take into account like thermal mass of the material.
No, we didn't take that into account. We neglected that, and like any heat gains from the sun, it's a very simple model. Yeah. But the material is pretty thin, so I think that as long as you don't have any like crazy ramps in temperature coming in, probably wouldn't be a huge effect. Any other questions? All right, great. Thanks.